Okay, welcome everyone back to LNG Academy episode 3. Before we jump in, I'd like to acknowledge a few things. First, the mission of LNG Academy is to spread LNG education across the world. We aim to be as factual and non-biased as possible and focus our discussion on technical issues with the hope that some of this knowledge will be beneficial to this great industry that we are very proud to be a part of and to contribute to. The opinions expressed in this podcast are solely based on those of the hosts. Speaking of hosts, that is a perfect segue to reintroduce my co-host, Mehdy Touil, LNG operations specialist. Mehdy, I would like to express to you and our audience that I truly value as a friend and colleague, and your presence on LinkedIn has truly inspired me. So merci mon cher mec.
Thank you, Alex.
Lastly, I'd like to thank the sponsor of this podcast, Capstone Industrial Training Solutions, who has recently joined the Solaris group of companies. Capstone are leaders in the LNG and industrial training space, and Solaris leaders in engineering, project delivery, and clean technology. For more information on Capstone and Solaris, please visit capstoneits.com and solaris-mci.com. Now, let's jump into our topic today, which is Cameron LNG, Train 4. Now, in the last few weeks, we've seen a lot of activity on the US LNG scene. The FID approval for Sempra Port Arthur LNG Phase 1, FID for Venture Global's Plaquemines LNG Phase 2, Freeport restart, etc., etc. Basically, US LNG is trending. Baker Hughes won a large order from Bechtel to supply its Frame 7 gas turbines and refrigeration compressors for the first 2 trains at Port Arthur LNG. Congrats to Baker Hughes. So, meanwhile, Sempra is focusing on Cameron LNG Train 4. So, what do we know about this project so far, Mehdy?
Thank you, Alex. So let's go back in time. In 2015, Cameron LNG filed with the US regulator FERC for the expansion of his existing 3-train facility with 2 additional trains, train 4 and 5, plus 1 additional storage tank. In 2018, Sempra signed a memorandum with Total to cooperate on US LNG projects and for the potential sale of 9 million tons per annum from the Cameron LNG Phase 2 project. In 2019, Sempra signed another memorandum, this time with the Japanese Mitsui, for the offtake of 1/3 of the plant capacity from Phase 2. In August 2020, when Cameron LNG Phase 1 last train 3, entered the commercial operations, Sempra announced that it could not give any assurance on the completion of its other LNG projects, including Train 4 and Costa Azul in Mexico. Remember, it was right at the start of the pandemic. In June 2021, Sempra announced that instead of going with 2 trains of 5 million tons each, it was decided to cancel Train 5 and focus on scaling up the capacity of Train 4 to 6.75 million tons per annum. The additional 160,000 cubic meter storage tank was also cancelled. In April 2022, Sempra awarded 2 FEED and EPC bidding agreement contracts for Phase 2, one to Bechtel and one to a joint venture between Japanese JGC and Zachry. Most recently, during its last earnings call, Sempra revealed that the FEED process with Bechtel will be completed in the summer of this year. So far, no indication was given on a potential final investment decision in 2023.
Oh, very interesting. Looks like Sempra has been quite busy. So, what was the initial design for Train 4 and Train 5?
Initially, the proposed trains would have replicated the design of Train 1, 2, and 3. That is Air Products propane pre-cooled mixed refrigerant process, the C3MR, with 2 Frame 7 EA gas turbines, one for the propane and HPMR compressors, and one for the LP and MPMR compressors. This is similar to other trains in the 4 to 5 million tons capacity range, like the Qatargas South ex Rasgas Train 3 to Train 5, Damietta LNG in Egypt, Peru LNG, or the new trains at Arzew and Skikda in Algeria.
Okay. All right. Well, we understand there is a design change for the new configuration. What is this design change? Can you expand on that a little bit?
The main design change was obviously the introduction of electric drive motors, or e-drive, to replace the frame 7 gas turbines drives for the refrigeration compressors, which are the main power consumer in LNG trains. The very first electric liquefaction facility was Equinor Hammerfest LNG in Norway, which uses Linde multi-fluid cascade process, or MFC, and Siemens 65 and 32 megawatt variable speed drive for the refrigeration compressors. Power for the plant is generated by 5 LM6000 aeroderivative gas turbines. The next facility that we covered in the LNG Academy episode 1 is Freeport LNG, with the 690 megawatt source from the state of Texas grid. There are other projects down the road, most of them in Canada. You have wood fiber LNG, Cedar LNG, Xylissims LNG, LNG Canada Phase 2 most recently, and also Papua LNG developed by Total. For Cameron LNG Train 4, the general project descriptions mentions that the intent of the design modification is to reduce the overall Scope 1 emissions, the direct emissions from the plant, by eliminating the frame 7 gas turbines and sourcing 300 megawatts of power externally. The output of the frame 7 at ISO conditions is around 87 megawatt, plus 12 to 24 megawatt coming from the helper motor. Train 4 will have a feed gas booster compressor to increase the inlet pressure to 68 bars, compared to 46 bar for the existing train 1, 2 and 3. Also, the dryer pre-coolers, which is a high pressure propane chillers, will be provided with a separate propane loop, including its own compressor driven by an electric motor, which is new. This is to allow the main propane system to be fully allocated to the liquefaction unit and scale up the capacity to 6.75 million.
Okay, wow. What is the new compression configuration, Mehdy?
So to maintain a proven size range, there is a restriction on the size of the electric motors drives up to 75 megawatt. It means that instead of 2 gas turbines driven compressor strings, the project will use the 3 electric motor driven compressor string. The first string will be for the propane compressor casing, the second for the low pressure MR compressor, and the third for the medium and high pressure MR compressors. Despite the change in drives, the liquefaction system process flow path remained the same as the original gas turbine design.
Okay. And what are the other design changes?
By eliminating the gas turbines, you reduce considerably the plant Scope 1 emissions, and you also eliminate the need for high pressure fuel gas piping and vessels. But also you lose the waste heat recovery unit that are included in the exhaust stack of the turbines. Most LNG trains use this lost energy to provide heating for the regeneration of the dryers and other process users, mainly reboilers, or to produce electricity using steam in the combined cycle assembly. In the case of Cameron LNG Train 4, gas-fired hot oil heaters have been added to the system to provide this process heating. The heaters utilize low-pressure fuel gas to heat the thermal fluid, which is circulated to the process users across the train. Also, without the exhaust of the turbines, you have to think about a backup for dumping the acid gas stream from the acid gas removal unit in case the thermal oxidizer, which is an incinerator, is out of service or under maintenance. The project will include a low-pressure ground flare to enable the combustion of the acid gas stream hydrocarbons. We used to call it the sour flare in Qatargas because of the high H2S content.
It's real interesting how a fundamental design change could cause so many ancillary effects. What about the CCS component, Mehdy?
So Cameron LNG is proposing a pre-investment tie-in on the acid gas inlet stream to the oxidizer on Train 4. In May last year, Sempra and its equity partners, Total, Mitsubishi, and Mitsui, signed an agreement for the development of the Hackberry Carbon Sequestration Project, or the HCS. The CO2 will be captured from Cameron LNG Phase 1 and Phase 2 and transported by pipeline to a compression facility. It will be then permanently stored in the saline aquifer using an injection well located approximately 8,000 feet under the surface of the Earth, with a capacity of up to 2 million tons of CO2 per year. However, FID for this scheme has not been reached yet.
Very interesting that we're seeing a lot of these carbon capture plants connected almost in tandem with the LNG trains. Very interesting. We've heard that several liquefaction plants in the US are having difficulties liquefying lean gas. Would that be an issue for Cameron LNG Train 4 as well?
It's an issue not only in the US but also in Australia and East Africa as well. Feed gas for Cameron LNG is supplied from the Cameron Interstate Pipeline, which is connected to 5 major interstate pipelines linked to the main markets in the US Midwest, Northeast, and Southeast. To meet pipeline specifications, gas producers tend to remove ethane and other components. It means that the methane-rich feed gas entering the liquefaction facility is low in propane, butane, pentane, and high in C6+, and other contaminants like benzene, toluene, and xylene. This is problematic as those will freeze in the cryogenic section of the train, but you don't have enough LPG to produce reflux and keep those contaminants at acceptable levels. You may need to reduce production or even shut down the train for defrosting in the most severe cases. You also need to consider your refrigerant makeup requirements. Cameron LNG predicted a wide variation in the NGL recovery rates, which is why the Phase 1 design introduced small and large fractionation units in a parallel arrangement and uses ethylene instead of ethane for MR makeup. Another method is to inject LPG to support better separation and alter the physical properties of the contaminants, a method already in use by some US plants to minimize the carryover of those contaminants. For the design of a C3MR train, you have 2 options: a scrub column integrated with the MCHE, which is an all-static equipment arrangement, or a standalone turbo expander NGL recovery unit. The scrub column operates at the same pressure as the MCHE, which is not optimum for lean operation, as liquefaction is more efficient at high pressure. For Cameron LNG Train 4, the NGL unit will use the open-art GSP process developed by Ortloff in the 70s, with dual reflux for enhanced NGL recovery, with the addition of a booster compressor to increase the pressure at the inlet of the MCHE to 80 bars as compared to 70 bar for the Phase 1 trains.
Sorry, did you say open art? I don't think I understood that one.
Yes, so similar to open source, open art in process engineering means available to the public, in opposite to licensed technologies. I would like to mention the economics of operating lean gas LNG facilities, which may come at a high cost. You don't have the benefits derived from the sale of NGLs and condensate, which are high-value byproducts. Below some gas price levels, your facility can become uneconomic. This is why efficiency is critical for lean gas liquefaction, and the high pressure allow for considerable savings in terms of refrigeration duty for larger capacities. If Sempra and its partners decide to move forward with the project, Cameron LNG Train 4 will be the industry's largest liquefaction train based on an all-electric configuration.
Amen to that. Well, we wish Sempra and its partners the best of luck in their Train 4 development. Thank you, Mehdy, and thank you for the audience again, and we'll catch you on the next episode.